So now let's talk about the coating failure. Now first let me plot a proper diagram for this situation. Okay. So our x-axis represents time, sliding distance, etc. And our y-axis represents VO. Now let me plot some sort of in this fashion. Okay, yeah. This is our coating zone. Okay, and so this is our coating, and this is our substrate. So this is our substrate material. So in this picture we can summarize the concept of coating failure with the symmetric cross section of our component. Here we can see the surface of our object where we apply coating, and below this coating we have substrate material where wear condition is pronounced on our external surface of our object. In this plot we compare qualitatively the typical three condition. Let me plot the condition here. First of all, yeah. So we have three conditions. First one is something like this. It goes something like this, the curve. Let's call this as A. The second one looks something like this, and then it goes like this. We call it B. And third one, mm, third one, let's say something like this. We call it C. So in the first one, that is in A1, we have no coating. So we have only the base material. On the vertical axis, we plot the wear rate of our material, that is the thickness which is removed during the service. On the x-axis, we represent the duration of our service condition with a wear stress. So in this first case, there is no coating, and we can suppose to have a linear consumption of our material, and we can see that as sliding time increases, we remove an increasing amount of our base material. So after a given time, we have removed the specified thickness of our material. So in this region, we have a relatively large wear rate. Now let's talk about B condition. So in the second condition, that is scope B, we apply our coating, and initially we observe the wear rate of our coating material, which is much higher in comparison to the base material. Initially we have a curve with much lower slope. Then after some time, as case A, the thickness of consumed material is much less, and we are still inside our coating. After a given time, the coating is consumed, and then we start as same wear rate as the base material. The net result is prolonged lifetime because we have achieved the same wear rate as the base material, that is case A, but after longer time compared to the uncoated material. Now let's talk about C. So the third condition is encountered when we have premature failure of our coating. So we start again with a lower wear rate behavior given by the presence of our coating, and after a given time we have some failure mechanism, for example detachment of coating fragments. Then we have a very high wear rate, particularly a vertical increase in the wear depth. Then we expose the base material and we might have the same slope as the original curve. Of course, the result is shorter lifetime in comparison to the second condition, that is B condition, because of the premature failure of our coating. In some negative cases, this detachment can produce higher wear rate with a higher slope in comparison to the base material. Anyway, the concept of applying hard coating is to reduce the wear rate as much as possible produced by our coating. If we have a coating material that is highly resistant to wear, the slope is very small, and we can prolong the lifetime by the order of the magnitude. So the key point of this approach is to produce the coating material able to provide a very high wear resistance. So what we can see that there are principally two modes by which our coating may fail, that is premature failure, and second one is failure due to gradual wear. So we have to synthesize a material. So we have to synthesize a material with exceptional properties. We remember that typically PVD coatings are produced in the thickness range of few micrometers. So this actual thickness is very low. In order to spend a long time with coating present on our substrate, we need an extremely high wear resistance. The alternative approach is to produce much thicker coating that can exhibit a lower wear resistance, because due to a larger thickness we can expect a longer lifetime. But for many applications it is not acceptable because thick coating changes the dimensions of our specimens. For example, if you think about our cutting tools, we cannot imagine applying 100 millimeter of coating which is not compatible with the geometry of our object. So we need for a sure thin coating. Then we have to synthesize a material able to provide exceptionally high wear resistance. So what are the most common failure mechanism of our coating? As we said, in many cases we must produce ceramic coatings that are definitely hard but technically brittle. So when we expose our component to a typical load external, we have a mating body on the surface with a significant normal load transmitted to our object or our system. Then in this condition, we have a possibility to produce cracking of our coating. That is, we'll observe these conditions. So this is our object or system, and we are going to get something like this. So this is a cracking of our coating. Cracks can propagate along the coating substrate interface, producing the fragments which are detached from our coating. As we said, this is a risk for 3-body view and is able to produce fast consumption of our coating. So we have to consider C condition with a premature failure and reduced lifetime. Unfortunately, the cracking condition is quite common because, as we said, we combine a soft substrate with a hard coating. So when we apply an external load, and if we have a thin coating, the normal load is able to deform the base material because we have a ductile soft material, and a thin material stress field generated by the normal load cannot be located inside our film, and then we have deformation on the substrate, that is soft substrate. So but our coating is typically not so tough, so ductile, and then in order to accommodate different deformation, cracks will form. The propagation of these cracks is quite negative for the wear resistance of our system. So capability to support the normal load, which is known as load bearing capacity, which we'll be studying in upcoming lectures, is the fundamental requirement of our system. So cracking and spalling of the coating may be the result of occasional or repeated excessive mechanical or thermal loading. Now we shall see the strategies we need to follow to arrest these issues in upcoming lectures.